Good afternoon, and welcome to the fourth week of facilitations on Physics 407, solid state physics. So, the last 3 weeks, we have dealt with the concept of dielectric properties of solids, in which we discuss what dielectric is and their properties. We also look at their responses in the electric field. Likewise, we also look at the polarizability, relaxations, dipole moments in the last 3 weeks. So, if you have any questions, you can ask me now before we move to new thing this week. Any questions? Any questions? Okay, in the absence of no questions, we shall go into a new topic today, which is mainly on magnetism. So here today, we are going to discuss what is magnetism, then the types of magnetism, where we are going to be looking at the diamagnetism, paramagnetism, and ferromagnetism, and antiferromagnetism. So now, magnetization. Magnetization of materials and how it's related to electric field intensity are just as the concept of how material responds to field. So a material substance acquires a magnetic polarization when placed in a magnetic field, just as a dielectric medium acquires an electric polarization in the electric field. So what we're trying to say is that last week, when we were looking at dielectric and electric field, today we shall be looking at magnetic field with reference to magnetic polarization. So the response of material to an applied magnetic field depends on properties of the individual atoms and molecules and on their interactions. So the orbital motion of electrons in atoms and molecules provide current which give rise to magnetic dipole. So in many materials, the small electric current associated with orbital motion and spin of the electron average to zero. So when such atoms are placed in a magnetic field, what happens to them? Electrons, minute electrons currents are generated by induction. Take note of that word. Minute electrons currents are generated by what? Induction in the cloud of electrons. So the direction of which is such that the magnetic field associated with them opposes the induced field, B, which is magnetic field. So these are known as diamagnetic substances. So there are other materials in which the atoms do have an intrinsic magnetic moment on account of the fact that the current from the orbital motions and spin of the electron do not average to zero. So although electron spins tend to pair and cancel one another, so there are atoms in which pairing is incomplete. When such materials are placed in the magnetic field, the magnetic moment of atoms and the induced magnetism enhance the external field. So the effect is more pronounced at low temperatures. So such substances are called paramagnetic substances. Likewise, every atom or molecule may be regarded as a tiny magnetic dipole with magnetic moment. So which is stated in equation 2.1. You see QLEIDS, where Q is the magnetic pole strength, L is the pole separation, and I is the current. ds is the area of the loop. So the effect of atomic magnets is described by a quantity called magnetization M, which is defined as the magnetic dipole moment per unit volume. So somebody can ask you, what is magnetization? The simple definition is the magnetic dipole moment per volume. So in many materials, it is found that magnetization M is linearly proportional to magnetic field intensity, which is stated in equation 2.2. That is M, magnetization psi of M, which is susceptibility and the magnetic field intensity. Now, What do we understand by diamagnetism? Can anybody tell us if you have an idea what diamagnetism is? Okay. Substances with a negative magnetic susceptibility are called diamagnetic. That is, when you have a material or substance that the magnetic susceptibility is negative, automatically the material is diamagnetic. So diamagnetism, to a greater or lesser degree, is a property of all materials and will always make a weak contribution to the magnetic response to magnetic field. However, for material that shows some other forms of magnetism, such as ferromagnetism or paramagnetism, the diamagnetic contribution becomes negligible. Substances that mostly display diamagnetic behavior are termed diamagnetic materials or diamagnets. Materials that said to be diamagnetic are those that are usually considered by non-physicists to be non-magnetic, and included, an example is water, wood, most organic compounds such as petroleum, some plastic, and many metals including copper, particularly the heavy ones with many core electrons such as mercury, gold, and bitumen. The magnetic susceptibility of various molecular fragments is called Pascal constant. Now, that magnetic material have a relative magnetic permeability that is less than or equals to 1. So we normally use this to classify materials into different magnetic types. So when you have a diamagnetic material, the magnetic permeability is less than or equals to 1. And therefore, a magnetic susceptibility which is less than 0, this means that diamagnetic material are repelled by magnetic fields. However, since diamagnetism is such a weak property, its effects are not observable in everyday life. For example, the magnetic susceptibility of diamagnets such as water is approximately minus 9.05 times 10 to the power minus 6, very negligible. The most strongly diamagnetic material is bitumen. So that has minus 1.66 times 10 to the power minus 4. Any question on that? Okay, now let's proceed. How conductors exhibit an effective diamagnetism? When they experience a changing magnetic field, the Lorentz force on electrons cause them to circulate around and forming eddy current. The eddy current then produces an induced magnetic field which opposes the applied field, resisting the conductor's motion. So the magnetic susceptibility per unit volume is defined as this, just like rearranging equation 2.2 and making the magnetic susceptibility solve the formula. Then you now have magnetization all over the magnetic field. So where M is magnetic moment per unit volume and H is the magnetic field intensity. So diamagnetism explains the tendency of electrical charge to partially charge the interior of a body from applied magnetic field. For an atom in a magnetic field, the motion of the electrons is the same as a possible motion in the absence of magnetic field, except for the superposition of a common processions of angular frequency. So putting this in mathematically, we have omega L, which is equals to minus EH, which is electrical charge, then divided by 2 M here is the mass and C is the speed. So the precisions of the electron distribution is equivalent to diamagnetic current, which is given in equation 2.5. Then by the time you rewrite it and equate it to each other, you have equation 2.6. So for Z electron, where rho is equal to x squared plus y squared is the average square of the perpendicular distance of the electron from the field axis. In terms of the mean squared distance from the nucleus, we have r squared to equals to this. So we can also rewrite the expression to have equation 2.8. So equation 2.8 is the Lagrangian expression that can be used to calculate diamagnetic susceptibility. Any question? Okay. Now, the exercises you need to lay your hands on are: one, explain all the symbols in Lagrangian expression and state their SI unit. Explain why the magnetic susceptibility of diamagnetic materials will always be less than zero. If you go through the concept of the lectures, you should be able to answer the two questions. Now, let's quickly look at paramagnetism. So far, we have discussed diamagnetism. Now, we will discuss paramagnetism, substance with a positive susceptibility. We said that diamagnetism are substances with negative susceptibility, but in this case now, they are substances with a positive susceptibility, which are called paramagnetic. So positive susceptibility may be found in one, all atoms and molecules that has odd numbers of electrons. Take note of those information. Two, all free atoms and ions with a partly filled inner shell, mostly the transition elements. Ions, isoelectronics with transition elements, rare earths, and metals. So paramagnetism is a form of magnetism whereby the paramagnetic material is only attracted when in the presence of an external applied magnetic field. What this is trying to tell us is that you cannot get a paramagnetic material without taking it into a magnetic field. There must be the presence of magnetic field before you can have paramagnetic. Once you take it away, it loses the properties. In contrast with this behavior, diamagnetic materials are repelled by magnetic field. So somebody can ask you to differentiate paramagnetism and diamagnetism. It's a simple thing is that in the presence of field, one attracts it, the other repel it. So paramagnetic material have a relative magnetic permeability greater than or equals to units. That is a positive magnetic susceptibility and hence are attracted to magnetic fields. So the magnetic moment induced by the applied field is linear in the field strength and rather weak. Paramagnetic material have a small positive susceptibility to magnetic field. These materials are slightly attracted by magnetic field and the material does not retain the magnetic properties when the external field is removed. So paramagnetic material properties are due to the presence of some unpaired electrons. And from the realignment of the electron path caused by the external magnetic field, paramagnetic materials include magnetic, magnetism, magnesium, molybdenum, lithium, and tantalum. These are examples of this type of material. Unlike ferromagnet, paramagnetic do not retain any magnetization in the absence of external applied magnetic field. Like I said earlier on, that you can only generate them when you put them in. If you want to take feed away, it loses the magnetic properties in the material. Some paramagnetic material retain spin disorder at absolute zero, meaning they are paramagnetic in the ground state. Thus, the total magnetization drops to zero when the applied field is removed. Even in the presence of the field, there is only a small induced magnetization because only a small fraction of the spin will be oriented by the field. This fraction is proportional to the field strength, and this explains the linear dependency. So the attraction experienced by paramagnetic material is non-linear and much stronger, so that it is easily observed, for instance, by the attraction between the refrigerator magnet and the ion of the refrigerator itself. Did you understand that concept? The practical experience of that is when you open the door of a refrigerator and you leave it, you go back and hook up again. The same thing when you look at the board, the white board we use these days with the duster. Immediately you put the duster on it, it stick to it. It is due to this property. Is that taken? Okay, fine. Any other questions? Okay. In the absence of no questions, I think we call it a day for today, and we continue from where we stop next week. In the meantime, try as much as possible to look at the lectures on the course page. I've uploaded all the videos so far the last 3 weeks. So hopefully today I'll also put this video online as well, so you can look through it and also try to read the lecture notes. So if you have any question, you are free to reach out to me. Thank you for coming. So see you next week.